Yeah.
No, that's not much.
Oh, all right, it is 9 o'clock. I'm gonna get started here. So did you guys have any time to finish up the disjunction gate implemented only using NAND 2 gates? Some of you did. That was at the end of the lab session. You know, I kind of left it up to you guys to implement the OR and a single OR gate having 2 inputs, but only using NAND 2 gates. Do you guys remember that? Yeah. So that was an exercise that I want you guys to go through, just so that you know how to get that stuff done. So what we'll do today is I'm going to go through the quote-unquote answer for that one first. There's nothing to turn in. It was not a homework assignment, but it was a suggested activity, just so that you can have something to do with LogicSim, and also, that will also help you understand the material that we have been talking on Tuesday. Okay, so there's that, and I'm just going to get the row sheet here for today and have it passed in class. All right, so let's go ahead and do that one first. I have the screen recorder already turned on. And today I'm using my, instead of using the whiteboard, I'm using a document camera. So since I'm using VLC to look at the document camera, this will also be recorded. So this is kind of like a new whiteboard instead of using this whiteboard. Is that okay? Yeah. All right. Okay. So the first thing we want to do is to figure out the math behind, how do we implement a OR, but only using NAND. Okay, so that's the math behind it, and then there's the mechanical part of, okay, now that we have this equation, how do we actually make it happen? Okay, all right, so we have, x. Now, since I'm writing, the downside of writing it like this is, when I'm writing, you can only see my hairy hand and not really what I'm writing, so I have to kind of remove my hand for you guys to see what I'm writing, or I can try to write in a kind of slanted way, so this way you can see what I'm writing. The alternative is to get that $600 Samsung Galaxy Tab S3, I think, that comes with a pen. Yeah, but that's a little expensive for this purpose. So we're talking about X or. Okay, do you guys want to use the double bar, or do you want to use just the double bar is fine? Okay, so we want to see, okay, what is this, right? So the first thing is, we can introduce double negation, because double negation does not change the value of something. So we'll say double negation, and then X or Y, just like that. Is that okay? That seems to make sense, because double negation is just kind of pointless. And then I rearrange the double negation so that we have a outer negation and an inner negation. I mean, that's just adding parentheses to emphasize which one is done first. It doesn't really change the meaning at all. I mean, it's just clarifying the ordering of the operation. So the next one is going to be the real trick of this thing is the next line, because what we can do now is to apply De Morgan's law. De Morgan's law is kind of like a distribution law, except it distributes a outer negation into something that is either a conjunction or a disjunction. Okay. So this is all being recorded, and let me just double check and make sure that the recorder is on. It is streaming, and we do have audio capture at this point, which means your focus probably is better off if you focus on what I'm talking about instead of trying to copy everything. Now I do kind of write and then talk a little bit, write and then talk a little bit. So if that pace is okay, go ahead and copy and write it on your piece of paper. But when it's too fast, like when I'm typing, then you might want to just focus on what I'm talking about and ask questions about what I'm talking about. Okay, so De Morgan's law let me transform this portion, okay, into something and something. So the OR, this OR here, has to be changed to an AND, but then the negation, which is outside of the OR, can be distributed to whatever I'm ORing. So this becomes not X, this becomes not Y. This is called De Morgan's law. It's one of the very, really useful transformation in Boolean algebra. You don't find this in any other algebras, but only Boolean algebra. All right. So once we have this, then we actually have this conjunction is negated by that exclamation point. So we have a NAND already. So now it is now becoming not X NAND. I'm just going to spell out NAND here, not Y. Well, but I don't want to use just negation because negation is not NAND. But we already know how to convert NAND into a regular negation because not X is X NAND X, or the negation of X and X. So that means now I can finish this one by saying this is X NAND X, and then NAND Y NAND Y, like that. So are there any questions about this particular derivation? Yes?
What do you mean when you say by negation?
Negation is not. So when we use the operator not, I call it negation because mathematically speaking, it is negating a Boolean value. Okay. Are there any questions about this particular derivation? This sounds more like math than it is programming, isn't it?
Yes.
But you should not be surprised because computer science is really a branch of mathematics. Okay, so when you move on to a 4-year university, there are usually only 2 places where computer science spins off from. It's either spinning off from engineering, particularly out of electrical engineering, or it's a spin-off from math. So it's coming from one or the other direction. Here is kind of special because it is a spin-off from business. Because we first started teaching application programs, how to use Word, Excel, and so on, and then gradually move on to teaching computer science and programming classes. All right. Okay, so given this equation, how do we convert this into the use of gates using LogicSim? Because this is our maker thing, right? We can test this using LogicSim and just play with it. So the way to do this is every time you have a NAND, or even the or even the not, those are all gates. Okay, what you specify as the quote-unquote input to the operator will become inputs into the gate, and then the result of the operator becomes the output of the gate. Okay, so when you look at this, you say, oh, okay, so X will feed into this NAND gate here. So you have X feeding into both ends of a particular AND gate, like so. So that this becomes this, okay? And then you have Y doing about the same thing. So you have Y, okay, there's supposed to be a bubble here because we are making a physical connection, okay? So this part becomes this here. So I would take the output of this NAND, which correspond to this wire and this wire, and feed it into another NAND gate, like that. And then this output becomes the actual expression. That becomes the actual output. So if I want to label these as input pins, they're squares. This one is an output pin. It is circular. So are there any questions about the solution to that particular problem? How to use NAND gates to implement regular OR or disjunction? No questions? It's all good? Okay. All right, so it is really a good time. This is a good time to kind of pause a little bit, look back, zoom out, and say, okay, what have we learned so far, but not the details. Okay, but the significance of what we have learned at a higher level. Okay, we now have negation, not, we have conjunction, and we have disjunction or. They can all boil down to NAND. Is that okay? But what is so special about NAND, other than, oh, we only need one single operator, it can emulate all of the other operators. There's one really cool thing about the NAND gate is it is one of the easiest gates to implement using transistors. So using only 4 transistors, 2 P transistors and 2 N transistors, I can implement a NAND gate. So at this point, we can basically say Oh, so that means all of the logical operators that we are familiar with can now be implemented physically using transistors. Is that okay? Now that is kind of significant because now we are tying in something that you learn in programming in an abstract way to something that can be physically implemented using transistors. Okay, all right, so there is that, and then we switch back to the browser and go back to Canvas, and then we are moving on to look at numbers now. Okay, now that we know how to deal with Boolean stuff, Boolean operators, and how to represent true and false by high and low voltages, now we go back and say, what about numbers? What about values and numbers that we have to process? Because that is a big deal too. Yeah, I can't get rid of the lab stuff, because it's just distracting to me. And then we go to the modules. So right now we are at the very end of physical states, truth, numbers, and computers, because this module does not actually deal with numbers. It only deals with the physical devices, and the only one that is important of all the physical devices are the transistors, because they are the current generation of computers are made out of transistors. And it is also important to understand this particular circuit, which we talked about in class on Tuesday during the lecture, and then we play with that in the lab session on Tuesday as well. Okay, so I'm hoping some of you find time to play with the Logisim, just to recreate the circuit, poke it, make sure it works, and so on and so forth, because that is the tool that you're going to use for the rest of this semester. Okay. And then the rest of this note here really is just looking at, okay, what if x is a 0, y is a 0, who is turning on, who's turning off, and so on. So at the very end of this discussion, there's a tiny little section here that talks about numbers and values. They're different. Okay, a number is a representation of a value. Okay, so don't say anything. If I hold my hand up like this and I ask you how many fingers, okay, what is in your head the concept that you counted the number of fingers? That is a concept of a value. But when I ask you and you have to answer the question and say, 4 in English, that is a number. In other words, a number is used when you need to communicate the concept of a particular value with another person, with a computer, or something else. But the internal representation of that quantity in your head is what the value really is. So other than 4, which is the word for this particular quantity, does anyone speak any other language in this class? Okay, many of you. So what is this quantity in Spanish? Cuatro. Okay. What about Russian? Okay. Japanese? Okay. What about Chinese, Mandarin? Okay, I don't speak Mandarin, but I can say in Cantonese it is say. Okay. Vietnamese, any? Yep. Okay. So in different languages, this quantity has different names. Those are numbers. Okay. It is a representation of the quantity. Okay. So this is how we transition to the next topic, or the next module, which talks about values, numbers, and bases, because now we can start to think about, to represent the same value, there may be different ways to represent exactly the same thing. So we can skip section 2, which is really just what I talked about a little bit earlier, that a number is a representation for communication purposes. So when you need to tell somebody, okay, let's say you go to a market, where you're on a tour, in a country where you don't speak the native language, so you want to know, how much is that thing, right? So you and the seller have to somehow establish a common understanding of quantities, and people just use fingers, right, most of the time. The next one, is going back to the caveman age and caveman age and talk about how we count and represent quantities back in those days. And then section 4 has a title that is, you may not have seen this before. I'm pretty sure you haven't seen this before because I made it up. Okay, I make up a lot of stuff in my classes. So it's called common base multiple digit numbers, which is no more than just how we usually represent quantities using our existing number system. Okay. So if you look at the example, okay, we'll use this one example here. 16.375. This is a decimal number. Don't worry about a binary at this point. So this is a decimal number. But what is the quantity that it is representing? What is in this particular value? So the first line expands all the digits out, like so. Are there any questions about this part? A fifth grader can do this, right? A fifth grader can look at the number and yeah, I can chop it up into its components. So by itself, it doesn't seem to have any significance. But when you go to the next line, then it has some significance. Okay, what is the big deal here? Okay, there's nothing new because 10 is simply re-expressed as 1 times 10 to the power of 1. 6 is re-expressed as 6 times 10 to the power of 0. 0.3 is expressed as 3 times 10 to the power of -1. 0.07 is re-expressed as 7 times 10 to the power of -2, and so on. But there's a regularity on the second line that is lacking on the first line. What is it?
Base 10 is expressed.
Some kind of, each term in the addition is a power of 10. It's a quantity times a power of 10. Is that surprising to you? It should not. It should not. But this illustrates what I mean by common base multi-digit number. Because each digit is telling you the quantity of a particular power of a common base. With decimal numbers, what is the base? 10, because we have 10 fingers. Okay? 10, by the way, is a terrible base. Okay, and I'll tell you guys why it is a terrible base later on, when we get to addition, subtraction, and stuff like that. So 10 is the common base, and this is a multi-digit number. 16.375 has got 5 digits. Okay. So then the question now is, well, if this is called common base, that means there are certain things that are not common base, but is multi-digit, right? Make sense? Okay. So let's go ahead and take a look at a base system that is not common. It is actually supposed to be pretty difficult to deal with, but then you look at it and go like, oh no, we can deal with this pretty easily. All right, so let's switch back to my document camera. Okay. I'm just looking at how it's not lined up correctly, and see if I can. Oh, okay. Nope, I think that's about as good as it gets. Okay. So let's just pretend that you're working, at McDonald's as a clerk. And by the way, those jobs are going away soon. Why do you think I said that?
Automation.
Automation, exactly. It's already happening. Somebody made a pizza truck, okay, that can make pizzas from dough and raw material from start to finish, fully automated. So when you combine that with Uber or Google's self-driving mechanism, that whole truck can be fully automated. Okay, at the beginning of the day, you just have to load it up with ingredients, make sure you maintain the engine, the tire pressure, and stuff like that, and send it out, and it will do the rest on its own. So jobs at McDonald's are going away. What are those people going to do? People who are currently working at McDonald's.
Become engineers.
Well, they have to be here to take classes first, right? Yeah, there was a hand.
Oh, yeah.
Yeah, go ahead.
I want to say the jobs in warehouses are replaced by robots because of the storage, stacking and everything.
is the efficiency of robotics in a warehouse setting is far better than using people. Because robots, you can design robot arms and retrieval mechanisms that are much more space efficient compared to a person who has to use a forklift and get things out of the shelf. Robots can do that much more efficiently.
Removing the parts of ergonomics.
Yep. So you have to kind of think about, this is out of the scope of this class, but you kind of have to think about, if this trajectory continues at an accelerated rate into the future, okay, more and more jobs that are currently done by people will be replaced by automation systems. And it will be more and more difficult for people to find jobs because we are not talking about a really big increase of the programming job market. It's not going to be increasing very rapidly. So where are these people going? So we kind of have to think about this. It's a social problem more so than it is a technical problem. It's just like back in the days when people transitioned from manual farming to mechanized farming. So one single harvester can replace a whole bunch of people working in the field. So what are those people going? They're not going anywhere. They're staying home. The government is paying them to say, okay, we understand that the machines are replacing you and you don't have a job anymore, but we'll pay you to stay home. And that's why in the tax law, if you report your own taxes, it will ask you whether you own a farm or not, because there are special considerations when you own a farm. But when you extend this to not just farming, but also other kinds of jobs, we are looking at a scale that we have never seen before, where people are getting replaced by machines and automation and robots in the near future. We are talking about a time frame of 10, 20 years at the most. Then we'll see a big shift of what kind of jobs are actually available, what jobs are going away. Your generation will see a bigger change than my generation. All right, well, getting back to this, what was I going to talk about? Oh, right, working at McDonald's. And somebody bought a hamburger and paid, use a $100 bill to pay for that, okay? So you have to, you have to give the person change. So it's going to be, let's say, $90-something of change. Is that okay? So the question is, do you know how to use the least number of bills and coins to have that change, instead of giving the other person 9,200-something pennies? Do you know how to use $50 bills, $20 bills, $10 bills, and so on? If you do, then you know base conversion already, because you're understanding something that is far more complicated than base conversion. Okay, so let me illustrate why I say that. Okay. So let's say the amount that you need to give back to the customer is $92, and I have to be careful what number I pick here. Yeah, 75 cents is good. Okay, there we go. So let's say we have to give the customer back this much money, and most of you already know that how to do this in an optimal way. Okay, so let's say, okay, what about $50 bills? How many $50 bills do I need? One. Okay, after that, how about $20 bills? Two. What about $10 bills? Zero. We don't need any $10 bills. What about $5 bills? What about $1 bills? Okay.
Is there a $2 bill?
Well, there are $2 bills, but I'm not taking that into consideration because it is unlikely that McDonald's will stock up $2 bills or half dollars, right? Okay, then we have quarters, 3 quarters, dimes, and what about nickels and pennies? Okay, missing a 0 here. Okay, there we go. So we have a number. This is a number.
Hey, Professor.
Yes.
Can we, instead of 3 quarters, we can use 1 50-cent coin and then 1 quarter?
But those are not common. So I'm only using the common coins and bills. Okay. All right. So I understand that we do have $2 bills as well as half-dollar coins, but those are very, very uncommon. Okay, so we have a number here. We have 12002.300. Okay, the point is always separating the units, how many ones from the fractionals, okay? But this is not common base, is it? Because when you look at, the jumps from one unit to the other unit, let's figure that out. From a penny to a nickel is a 5. From a nickel to a dime is a 2. From a dime to a quarter is a 2.5. It's not even an integer there, okay? And here's a 4. And at this point, we don't even have a recycling or have a repetition of these numbers, 5, 2, 2.5, and a 4. And then we have a 5, and you might think, oh, okay, so that means we are recycling all of these numbers. We have a cycle now, because the next one is a 2. Ah, cool. But then we don't have a 2.5 anymore. We have a 2, right? And then we have a 2.5 here. And the next one is going to be a 2, and then another 2, and so on. So there's no regularity. It's not a common base. And yet you know how to deal with it. I don't get it. How do you learn to deal with this? Experience. You have done it many, many times, many years of experience. So intuitively, you know how to do this already. How many people feel confident that you know how to do base conversion from base 10 to base 2 and any other base? Okay? So only a minority of people feel comfortable, but yet you can do this. Okay, that's logically inconsistent. Okay? All right, so why is this inconsistent? Let me take this out. And then we'll start with the same value, okay, which is $92.75. $92.75. But this time I'm going to use an imaginary currency system because we're now in the country, which is kind of odd because people only got 2 fingers. Okay? Hoofs, that's it. Okay, that would work. Okay, hoofed animals, they don't have fingers because they're all fused, so it's either 1 or 2, right? So it's binary. Okay. So in that particular country, totally imaginary, and there are mythical animals that only have hoofs, right?
Pegasus,
Lots, yeah.
Stuff like that, yeah.
Yep. Okay, so we have $1 bills, and then we have half-dollar coins, then we have quarters, and then we have 1/8 of a dollar. On the other side, we have $2 bills, $4 bills, $8 bills, $16 bills, 32, and 64, and 128, and so on the other side. But you get the idea, right? They're all powers of 2. Positive, non-negative powers on this side, and negative powers on the other side. Okay? All right. So then I say, okay, using these particular values, do you know how to make change for $92.75? And most of you go like, yeah, we can do this, because if you can deal with the previous system, which is totally irrational, okay, there's no irregularity to it. This one is extremely regular, okay? It has a base of 2, right? So, but how do you go about doing it? You look at 92.75 and you compare that to, you want to get the largest power of 2 that is less than or equal to that number. Okay, so out of these numbers, 62 fits the bill. Okay, so you say, I'm going to pick out 164. So after you take a 64, how much is left?
28.
Okay, so you have 28 and 75 left. So you don't have any 32 because so you go to 16, you take 116, so you get 16 out of this, you get 12.75. So you will need an 8, right? You subtract 8 from it, you get a 4 point something, you take a 4, then you don't need a 2, you don't need a 1. Okay? And then you look at a half, you go like, yeah, well, I'll take a half. And then you take a quarter, but you don't need an 1/8 anymore. Is that making any sense? Okay? And guess what? You just converted a number from base 10 to base 2. And where do we put that decimal point, or binary point in this case, because it's a binary number? Between, yep, 1 and 0.5, because the binary point or decimal point or whatever base you want to use, the point, is always separating the base to the power of 0 from the base to the power of something that is negative. is indicating what is where the power of 0 is. Okay? So when you look at this number here, oops, here we go. When you look at this number, it's a binary number. You have just done your base conversion. See how easy it is? Do you think we should change our currency system to binary? I say yes.
You just use dimes and it's just dimes and just drop the pennies place wherever it's called.
So you want the base, you still want base 10, right? You know, dime to a dollar to $10. But then you need to know division to get it to
You
work.
get a 50-cent piece and a dime for change. And that's all.
Say again?
You do a 50-cent piece and a dime for change, and that's all. If you drop the ones place.
Oh, okay.
Yeah, it's the most popular coin.
The quarter, right?
Yeah.
Yep. But I think a binary system works much better.
Yeah.
Now the best thing about the binary conversion is that you don't need division at all.
That's all.
Now if you want to convert it to base 3, you need division because you need to find out how many powers of 3 you need for each particular digit. Okay? But for binary, it's easy. It's a comparison instead of a division. Is this number greater than or equal to 64? That's the only question you need to answer. You don't need to know how much it is bigger. You don't need to know how many 64s fit into this number. You just need to know, is it bigger or not? Is it greater than or equal to? Which is a whole lot easier to answer than, in our monetary system. It's like, okay, how many $10 bills do I need, for $30.65? Then you need to do division. 30 point something divided by 10 is 3. Okay, $3 bills. Yep.
But wouldn't you have more variety of coins in that case?
Yeah, you do have a little bit more. But the other thing that's nice is you only have 1 or 0 of each type of bill or coin. Whenever you need to specify a value, you just need 1 or 0 of each type. There's no cases where you need to say, okay, here's 3 $10 bills and 5 $1 bills, quarter, 2 dimes, and 1 penny. Okay, it is a whole lot easier to deal with.
You get a lot of different types of bills.
Hmm?
You have a lot of different.
Yeah, you get more
Once you
types of
get-
bills. Yep.
Once you get past like if you maxed out your dollars at 64,
Yep.
then you have like to pay a $300 thing. You still have to use multiple bills.
Yep. You have more bill values to deal with. Correct. Yep. But most of us, only go up to 128 and we are good. It's only with people like Elon Musk or Bill Gates or those people, they need to have a variety of bills.
Yeah, okay.
To the common person, it doesn't really impact us all that much. All right, cool. So we have done the base conversion. So with a common base multi-digit number, the value, which is V, expressed by the number. So D subscript I is indicating the value of a particular digit. So I is the index of the digit. So we start with 0. Okay, D0 would represent the quantity of a base to the power of 0. So that's why you see I being an index, going from negative infinity in theory to positive infinity in theory. But what we do here is we multiply the digit, okay, the value of a particular digit at place I times b to the power of I, b being the base of the system that we use. And then you just take the summation, and that becomes the value represented by a number in base b. Okay, what can b be? Well, we deal with base 10, so to us, b is usually 10. But when you're dealing with computer science and the interior working of a computer, b is usually 2 because it's binary. But no one says b cannot be some really oddball numbers like 7. Why would you use 7 as a base? I don't know, but it's possible. Of course, just because it's possible doesn't mean it's a good idea. Okay. So section 5 talks about the other way around. How do you convert a value v to a number in some particular base? So it's going backwards. I'm skipping this section for now, okay, because we don't really have a need for general purpose conversion into a particular base into any arbitrary base. Binary is basically what we are mostly concerned about. So I'm going to skip this section for now and just skip all the way to binary numbers. And binary numbers means that the base is 2, and that's why b equals to 2, using that equation that we had earlier. Using this equation earlier, b is 2 in this case. And the conversion process is a whole lot easier because it only involves comparison. Okay. So the next question is, how are values represented in a computer? So when you store something into an integer type in C and C++, how is it represented internally? It's in base 2. Okay? Everything is represented in base 2. But in C and C++, when you use cin into an integer, you type in base 10 numbers, right? So what's going on here? Cin is doing the base conversion for you. Okay, it is converting what you type, which are basically digits in base 10, into the binary internal representation. So there's an internal conversion process that is hidden from you when you use cin to read something into an integer type. Okay, so here's an exercise for conversion. So it's a suggested activity, but you don't have to do it. Okay, so we are moving on to adding binary numbers. Are there any questions we proceed to talk about binary number addition? Like, what is a base? How do we convert bases? We are mostly concerned about just a base 2 at this point. So just kind of focus on base 2. Are there any questions about how numbers or how values are represented in base 2? Not yet? Okay, that's fine. Not a problem. Okay, so we'll go ahead and start with adding binary numbers. And we'll start with general adding in base 10. So the question is, okay, so instead of reading my notes, which is really boring, even to me, I wrote this stuff, so it's particularly boring to me because I have seen it already. So instead of doing this, I'm going to switch to the documents camera. And then we'll start with some really boring examples. For addition. So I'm going to ask you some really simple questions, like what is 3 plus 4 in base 10? So unless I tell you it is of a different base, the default is base 10. What is 3 plus 4? I mean, you guys can do it right away. Oh, it's 7. How do you know it is 7? At this point of your life.
Drills and shortcuts.
Exactly, it's a lookup table, right? You look at 3, you look at 4, it's in your cache. This stuff has been cached for many years, right? Okay, cool. But what about somebody who's in? Do they talk about addition in elementary school? Yeah, first grade, second grade, or so. So to a person in first grade, how do they know that 3 plus 4 is 7? They count. They count either using fingers or blocks or something like that, right? So when I was a kid, I remember, because this is all tactile, they give us blocks. So you will have a block of length 3, and then you'll have a block of length 4. So when you want to figure out what is 3 plus 4, you put those 2 blocks right next to each other. Okay. Then you count, right? You go 1, 2, 3 from the first block, and then 4, 5, 6, 7 from the second block. You say, oh, so the sum is 7. Okay, so that's how we learn that 2 plus 5 is also 7, 1 plus 6 is also 7, and so on. Yes?
But there's another thing cached into that the order of counting.
Yes.
With base 2, you don't have order of counting, right?
Order of counting.
Like, you just have higher base multiplication of the same base, but just to comparison. You don't have to think about where is 1 and where is 7.
You're still adding, but I'm just talking about how we learn all of these things, and how many of these things have you learned? Now, at this point, you might say, oh, it's easy. I know. Okay, let's talk about the next one. What is 4 plus 8? Oh, 4 plus 8, is more than 10. You cannot represent it using a single digit anymore, right? So your teacher tells you in first grade or second grade and say that if it's more than 10, then you use a 1 to represent that you have a 10, and then whatever is left is what you do with the first or the least significant digit. So with 4 plus 8, I like to write this as 2 with a carry of 1. So instead of looking at this as 12, which is correct, I look at this as 2 with a carry of 1, because this way I can carry on multi-digit addition. Okay, it's just handy to look at it this way. But nonetheless, how many of these entries have you memorized? Let's look at the table. Okay, so let's look at the table. It goes from 0 to 9, goes from 0 to 9, and then each entry is basically, you know, this plus this. So you might say that, oh, but there are certain entries that are completely trivial, right? Because 0 plus anything is that anything, and then anything plus 0 is the same thing. So you don't have to memorize these particular items because they are trivial. Fine. And then somebody will point out that and say that addition is commutative. Okay, your 2 plus 5 is the same thing as 5 plus 2. Okay, so you can say, okay, half of these entries, because it is a mirror, this line represents a mirror of symmetry. So half of these items you don't have to memorize because it's the same as the other half. Can't do the same thing with subtraction, by the way, because subtraction is not commutative. So you still end up with, I don't know, maybe 30-ish or 40-ish items that you actually have to memorize. Okay. Now, if you have a younger sibling or a nephew or a niece or a kid of your own at about this age of your first grade to second grade, how long does it take to master addition, just addition itself? It takes a while, right? Certainly not something that, you know, kids can master in a day or two, because it takes a lot of practice in order to map. Oh, 3 plus 4 is 7. 3 plus 4 is 7. Instead of having to count, you know, in order to be able to do it without counting, without looking up something, it takes a lot of time to memorize all of these things. Does that make any sense? Now, to us, you know, we have forgotten how difficult it was to, you know, to memorize, you know, how to add numbers, because it has been a long time for us, particularly long for old people. Because it has been like 40-something years ago, okay? But when we were learning this, it is not easy. It was not easy. Is that okay? All right? All right. So if I were a politician and I want, you know, votes from future voters, like, you know, the current, you know, first graders and second graders, the first thing I would propose is to switch our numbering system from base 10 to base 2. And I can guarantee voters, okay, and once I illustrate the following. So let's switch to binary numbers and then look at the table of adding, okay? You go like, whoa, that's a pretty big table. No, it's not a big table. Okay. 0 plus 0 is 0. Do I really need to explain that? Even to a first grader, you would say, okay, you got no candy on this hand, you got no candy on the other hand. How many candies do you have in total? They can tell you. Are you trying to suck on me? Right? You know, they know right away. This is an easy to grasp, you know, concept. Is that any different from base 10 or any base? You got nothing on one hand, you got one thing on the other hand, and you ask, you know, how many things do you have total? Okay. Same thing, you just switch your hands, right? Right hand versus left hand. The only one that is a little bit tricky is this one. Because now you say, well, only got 2 hoops, right? I don't have fingers. So, you know, how do I represent, you know, 2, or the quantity of 2, the value of 2, but not using 2 as a digit? It's 1 0, exactly, because it is 1 0 in this case because it is 2 to the power of 1, okay? Because the 0, the number of zeros tells you, you know, what kind of power you're dealing with. So when we have 1 equals 0 to the right-hand side of the 1, that means we're dealing with 2 to the power of 1, which is the quantity of 2. Okay. So at this time, I'm going to add some leading zeros to each of the other ones, which would not change the value that they are representing, but they're kind of important. Okay. Are we doing okay so far with this addition table? Do you think no questions? Okay. So do you think this will be a good platform for me as a future politician? If I go to the first graders and go like, if you elect me as your future president, well, I cannot be a president because I wasn't born here. But I can be vice president. So I just have to pick somebody else to run with and say, and I say, okay, if I change, from this to this, would you elect me as your vice president? Yes, absolutely. Because there's no memorization. You can master the table itself in a few hours. Okay? Now, how does that have anything to do with this class? Well,
Binary and assembly.
binary, because inside the computer, everything is binary. Okay? We only care about whether there's a high voltage or low voltage, whether a transistor is on or off. So the computer instinctively or just natively, naturally, only use binary numbers. So if you want your computer to do any type of computation, okay, most computations involve addition or subtraction, you need to know how to perform addition in binary. And that's why we are getting this done. Okay, that's why we need to talk about this particular topic here. Okay, so switching once again from this topic, we are switching back to multi-digit addition, but in base 10. Okay, so this time I'm going to introduce a function called R, which is the result of addition, and another function called C, which is the carry of a particular addition. Okay, and I'm going to use a few examples here. I'm not going to exhaustively list all the possible cases because there are too many. So, but this is all in base 10. So let me emphasize this is all in base 10. We have X, we have Y, and then we have the R, which is the result of adding X and Y. And then we have CXY, which is the carry of adding X and Y. X can be only a single digit, and Y can only be a single digit, in base 10 in this case. So let's start with some really easy stuff, like 3 plus 4. 3 plus 4 has a result of 7 and a carry of 0. 4 and 8 has a result of 2 and a carry of 1. Okay? 8 and 8, 8 and 9, okay, has a result of 7 but a carry of 1 because it's 17. So are we okay so far with what I consider as quote unquote the result of a single digit addition and the carry of a single digit addition? This is all in base 10, by the way. Is that good so far? All right? Okay. I'm just introducing the notation of R and C as functions. Okay. So with this notation, then I can start to say, okay, how do we perform multi-digit addition, but look at it from a abstracted perspective. Now, before we do any type of abstraction, it always helps to do one single example that is concrete so that we remember, oh, okay, so that's what we are talking about. So we'll go ahead and use this as an example. 586 plus 100 and let's make this fun. Okay, there we go. Okay, so I'm trying to carry out this particular addition, and of course you guys know how to do this already, but I want to point out the really important components of this, okay? Because a lot of times when we do something like this, we do a lot of stuff in our mind without actually writing it out. So I'm going to write out everything, okay? So I go like, okay, what is 6 plus 6? If we look up this table, 6 plus 6 has a result of 2 and a carry of 1. Okay, now there's an implicit 0 here. The implicit 0 here is representing the fact that we don't have any less significant digits. So there's nothing that will contribute a carry to the 6 plus 6. It is implicitly there. It's just that most of the time we just ignore that because why would I want to waste time to add a 0 to something? But it is implicitly there. 2 plus 0 is a 2 with no carry. We doing okay so far? Okay. So I'm going to move this carry over here. So I'm going to dedicate a particular row for carry, and this is the sum, and this is kind of an intermediate result. Okay. So I move on to the next column, 8 plus 1. 8 plus 1 without this 1 here is actually just 9 by itself. Does it have a carry to contribute to the next column? No, not by itself. And then we have 9 plus 1, this one being the carry from the digit 0, or the digit at position 0. 9 plus 1 is a 0 with a carry. I put the carry here. And then with the most significant digit here, 5 plus 1 is a 6. Does not have any carry on its own. 6 plus 1 is a 7, also does not have a carry. So now I have a result of 702 by adding 586 to 116. So you know how to do this addition already, but I spell out every single step, no matter how minute it is. Now, why do I need to spell out everything?
You're about to change. You're going to use that idea in a different.
Exactly. I want to abstract it so that it can be applied to any type of base, and it can be done mechanically. Now, anytime you want to automate something or mechanize something, you have to know all the steps. You cannot just say, oh, in this case, we can skip that. Because when you're trying to tell a computer to do something, it is always helpful to have consistent, repetitive steps that are universal, single. They're the same for everything. So that's what I'm trying to do here. Okay. I still have a little bit of space here. So if I abstract this here and say that, okay, let's look at the first number and we'll call that x. In particularly, I will use x0, x1, and x2 to denote the digits. Okay, x0 being the least significant digit, x1 being the second least significant digit, and in this case, x2 being the most significant digit. And I will do the same thing with the 116. I'm going to use y to represent it. So there'll be y0, y1, and y2. Okay? So now I want to say, how do I utilize R and C to spell out how addition is performed? Okay? What do you think? What do you think this 2 is corresponding here? What is going to be that thing?
Yep.
Exactly. So this thing, okay, I need a way to kind of drag it out. Okay, maybe on a separate piece of paper. Hold on a second, let me try to do this way. There we go. Low tech, but effective. Okay. So this thing becomes R, the result of adding the digit x0 with the digit y0. Okay. This one we can just kind of give it, say that it's given to be a 0. Now, if this is given a 0, then this thing is going to be the same as that thing. Okay. So for now, we'll just say that they are the same. Is that okay? What about this one?
It's going to be R, x1, y1 plus c, x0, y0.
There's no plus in this case. This one is just r, x1, y1. Because it's the partial sum. Now, this one is going to be a little bit more complicated because it's a carry. Okay? But it's not a complicated carry. It's the carry of adding x0 and y0. Because this is also a 0, we know that cannot contribute to this carry here. So when we look at this, or the actual digit in the sum, what is that going to be? It's going to be the result of adding this thing, which we know as r x0, y0, with this thing here, which we know as c x0, y0. Does that make any sense? Okay. What about this one here? This is an easier one.
That's r x2, y2.
Yep, it's r of x2, y2. So anything of this row, okay, I'll call this row Q, okay. So anything of this row Q is pretty easy because it's really just the partial sum of a digit from the digits of the two numbers that we are given. Okay, so this one, pretty easy. This one is just r of x2, y2. This one now gets a little bit complicated, doesn't it? Yep, go ahead.
I can help but notice the one before it is result of r x1 y1.
Yes.
Shouldn't that be true? Like, to the
Result
carry.
x0, y0.
Oh, okay, sorry.
I thought that would come back.
Yep, this is r1, x1, y1. Sorry about that. There you go. Okay. So getting back to this particular thing, which is the carry, this is not going to be a very simple carry because there are two things that can contribute to this carry. Let me illustrate which two things and see if I can find a pen of a different color because it will certainly be helpful. In this case, okay, there we go. We got a red pen here. It is not cooperating. Okay.
Want a blue pen?
Yeah, I got a blue
Obvious.
marker thingy. Okay. It will work. Okay. So there are two things that can contribute to this particular carry because the addition of these two digits can contribute here. But the addition of these two can also contribute here. Is that okay? So we have to be careful with this one. So this one turns out to be, so let's go ahead and list each component first. And then we'll think about how do we combine the components. So one component is the carry of adding x1, y1. So C x1, y1 is one component. The other component is adding this thing here and this thing here. Now this thing by itself is r x1, y1. And then the other thing is this one here, which is by itself a little bit complicated because when you follow the lines, it is C of x0, y0. Okay. Okay. So now we have this component that can contribute. We have this component that can also contribute. So how do we combine these two components so that we end up with a single value that we can put here?
Result of first carry with the second carry.
Huh?
Result of the first carry with the second carry.
You can just do a single add, right?
Yeah.
Addition would do just fine. There we go. Okay. So now in this notation, things are pretty. They will get out of hand pretty quickly because I'm expanding everything, as much as I possibly can. Okay. So the notation of using a Q, okay, Q to represent this row, and then a K stands for carry to represent this row, can be very handy. Okay, so if I switch to the Q and the K notation, things get a little bit easier. Okay, and this is the sum row. Okay, so the sum row is actually a lot easier to deal with now because we can say sum I, Si, which is the digit I of the sum, is going to be the R, the result of adding two components. Which two components are we talking about? Qi and Ki. Right? If I label, these items, these three as Q2, Q1, and Q0, these three as K2, K1, and K0, then the sum is pretty easy to deal with because I don't have to go all the way back to the original Xi and Yi. Is that okay? What about Q itself? Qi. That's also pretty easy because Qi is the result of adding the digits from the original numbers, which is Xi and Yi. Is that okay so far? What about K? K is the more complicated one.
It's I minus 1.
So I would say Ki plus 1, okay, so that this way I don't have to deal with minus 1 on the other side because there are more items on the other side. So I'm lazy. Okay, so Ki plus 1 is going to be what? In general, the carry of adding Xi, Yi plus the carry of the result of adding Xi, Yi and the previous carry. But we know the previous carry is just Ki. Done. So by looking at the generalization, the template, we now have this kind of equation. Is that okay?
It's think it's just crazy.
Well, it's the same thing that you have always been doing with multi-digit addition, but I re-express everything in a way that is much more formal, not ambiguous, and we can easily turn this into binary now. Because all we're going to change would be the functions R and C. If you change R and C to the result and the carry of a binary addition, these equations stay exactly the same. So is that okay so far? Cool? All right? Okay. So now we switch gear again, looking at the R and the C, but from the binary perspective. Okay? So we have x, y, R, x, y, and then C, x, y. Okay? But this time they're binary. Okay, let me align everything first before everybody tilt their head and get neck injury because of this class. Okay, that should be all the cases for binary numbers, right? Because x is a single digit of a binary number, y is the same way. So if you have two independent variables, each one can only be a 0 or 1, then this will account for all the possible inputs. Is that okay? So we look at the R first, the result. Okay, 0 plus 0 has a result of 0. 0 plus 1 has a result of 1. 1 plus 0 has a result of 1. 1 plus 1 is the only tricky one. It has a result of 0 because it has a carry of 1 in base 2. But the other three cases, they would have a carry of 0 because they don't need to carry. These values can be represented by a single digit in binary. Is this table okay so far? Looks okay, right? Okay. So if you kind of look at the 0 as false and the 1 as true, then you look at this table and go like, hey, that carry thing kind of resembles a particular operator that we have used quite often. Not NAND, just regular AND. Okay, very good. Good job. So when you look at CXY in a binary math setting, you can just say that if I look at a 0 as false and a 1 as true, this is really the same thing as x and y. It's identical, right? But this is a significant step because now you are changing, you are implementing an arithmetic function using Boolean functions or Boolean operators. But okay, what is the big deal? Okay, arithmetic versus Boolean. Okay, fine. What is the big deal? But Boolean stuff can boil down to NAND gates. NAND gates can boil down to transistors. We can do this with transistors now. That is the significance. Okay, but I bet you cannot do it to R, because R looks like kind of complicated. We don't have a single binary, we don't have a single Boolean operator that can do R. Exclusive OR can do that, okay? But let's say we cannot use exclusive OR, okay? So we'll give ourselves a challenge and say that what if exclusive OR cannot be used? So you can look at the result of adding x and y and go like, there are two rows that have a result of 1, and then the other two rows have a result of 0. So if I just look at each row where the result is a 1, and I say, okay, I'll make a sub-expression so that when x is 0, y is 1, the result will be a 1. I'll have another sub-expression. Just hold it 1 second. I'll have another sub-expression so that when x is 1, y is a 0, the sub-expression will also give me a 1. And then we OR these two things. That should give me the result that I need. Yes, go ahead. Well, mod is a very complicated arithmetic operation, so we don't want to do mod. Yeah, mod implies a division, so that's actually pretty complicated. Okay, so let's look at the two sub-expressions. So we want one sub-expression so that when x is a 0, y is a 1, the sub-expression itself will give us a 1. What about this? What about not x and y? Okay, when you look at not x and y, then the not x will turn this 0 into a 1, and then y is already a 1, 1 and 1 is a 1. So this sub-expression will give us a 1 for the second row. Cool. And what about the third row? x is a 1, y is a 0, we can use the same strategy, can't we? X and not y. So one sub-expression handles row 2, one sub-expression handles row 3, and then we say, let's put an OR here. Then we are done, okay? But in engineering, electrical engineering notation, we can simplify this to just, not xy plus x not y. That's just a notation thing. Is that okay so far? Do we know how to do negation using NAND gates?
Yeah.
Let's go ahead.
What if we cannot use that OR? What if we cannot use that OR? Right.
What do you mean by we cannot do that OR?
What if we cannot use the notation OR in the expression?
We cannot use.
Like a scenario would be that you're not allowed to use OR in any case.
Well, but we can boil a OR down to NAND gates, so it's okay. So the idea is, we are boiling things down to transistors as much as we possibly can. Okay. The negation, we know how to do negation using a NAND gate. We did that during the lab session on Tuesday. We know how to do the conjunction in NAND. We also did that in the lab session. And today we talk about how to convert an OR into NAND gates. Now, is it complicated? Well, sort of. I mean, it introduces a few more components and whatnot, but it's possible. In other words, this can also be done in transistors. That's the bottom line. Optimization is not a big deal in this class, okay? But the concept, the idea of this can be done using transistors is important to us. Okay, great. So when we substitute C to be this, R to be this, then we have binary addition using the same structure, using the same construct that we have talked about earlier. Let me go back to that slide. Where did I put it? Oh, right there. So once we look at C as a conjunction or an AND gate like this one, and once we look at R as a whole bunch of gates, 2 AND gates and 1 OR gate, because we can negate the input to an AND gate individually. I'll show you guys how to do this in LogicSim, by the way. Okay, so in the lab session today, I'm going to implement all of the stuff that we talk about in theory in the lecture, but we'll do it in LogicSim so that we can actually say, oh, we can make an adder just like this. Okay. But the bottom line is, once we know how to perform the C operation or the carry function and also the result function using these logical operations, we can plug those back in to these 3. Then we can perform multi-digit binary number addition. Is that okay? Are we making those connections? So we talked about multi-digit addition. We use a base 10 example. Then we abstract out the mechanism and boil everything down to these definitions, right? And then I switched gear and talk about just binary addition. What is the result? What is the carry, right? And then we go over how to implement R and C for binary numbers using logical operations. So now we combine the logical operations for binary addition R and C with the general framework of multi-digit addition. Now we can make components. We can make actual electronic components to perform multi-digit binary addition. Are we making those connections? Okay, because it is those connections that really matters. Because when you're trying to understand something, it is really helpful to have a kind of zoom out view of how the big pieces connect. And then you can, once you know that, oh, this piece connects to this piece, then you can focus on the details of how those two things connect. But if you don't have a big picture, then you're just randomly wandering around, and it becomes much more difficult to make sense out of the different concepts and topics. So are we doing okay so far, or are there any questions? This would be a good time to ask questions about all those things that we have just talked about. No questions? Let's go ahead and do some binary addition then. Okay. All right, so we'll do some binary addition. We'll start with something that's relatively easy, like that. Okay, this is all in binary, so I use a subscript 2 to indicate these are binary numbers. And I'll use the same rows. Okay, so this is row X, this is row Y, this is row Q, this is row K, and then the row S is the actual sum. Okay, 1 plus 0 has a partial sum of 1. The implicit K0 is a 0. It's just kind of given. So now we know that neither contributes a carry. So this carry K1 is going to be a 0. 1 plus 0 is a 1. Are there any questions about the first column, the least significant column? Second column, 1 plus 1 is a 0. Remember, this is R of these two digits. But this guy here is the sum of the addition of these two and the addition of these two. Well, we know this is going to be a 1 already, because this 1 is contributed by 1 plus 1, like that. 0 plus 0 is a 0. 1 plus 0 has a partial sum of 1. It does not contribute to this carry just yet. 1 plus this one, which is a carry from the previous column, has a result of 0, but this one now contributes to a carry to the next digit. 0 plus 0 is a 0, does not contribute anything to the next carry. 0 plus 1 is a 1, also does not contribute a carry to the next item. But we do want to denote whether we have an overall carry or not. Now, the reason why we want to denote an overall carry is because when you're dealing with a 4-bit adder, then you only can use 4-bit numbers as inputs, as well as the output. So when you add 4-bit numbers, the input X has to be a 4-bit number. The input Y has to be a 4-bit number. But the output, which is sum, S, also needs to be a 4-bit number. Well, but what if we are adding something that cannot be represented using 4 bits? Then you have an overall carry, which is this one here, that is going to be a 1. So you will remember that the result of the previous addition cannot be stored using only 4 bits. But the actual result of the sum is only 4-bit 1. Are we doing okay so far with all this stuff? Okay. Don't you think this is a whole lot easier than a base 10 addition? Now, some of you might be thinking, no, this is kind of, I need to work really hard to understand this stuff. That's only because you have developed a bad habit of using base 10 addition over these, over all the years. You just have to undo all the bad habits and rethink about the good habits using base 2, then you'll be fine.
Just relearn it.
Well, you keep the portion where it reapplies to base 2.
Yeah. You
just have to ditch the table that you have memorized. Yeah. So all that memorization, for a good, like a few months in 2nd grade, is just going down the drain.
Also the use of 8 characters.
Hmm?
Also the use of 8 characters.
8 characters.
2, 3, 4, 5, 6, 7.
Right, exactly. It uses fewer digits. Yep. Mm-hmm. You need 0 and 1. So you cannot be. They cannot. Your teacher cannot say bad penmanship nearly as easily. I can't tell whether there's a 4 or a whatever, right? Yep.
If you had a base number system that didn't have any other numbers than 0 or 1, you couldn't say. How would you display if it's a base 2 number system? If it was 0 and 1. How would you display 2?
Well, if it's a base 2 number, you use a subscript of 2.
No. I was thinking about theory-wise. If you have a civilization's base number system is base 2, and they have no other numbers, how would they say this is base 2?
Well, within that civilization, we by default, base 2 already, so they don't need to have a subscript to indicate it's a base 2.
You don't have to have a number saying 2.
Yep.
So
say base 10 or something.
Well, they will need to use they will need to use base 2 as a subscript for any other base then. Just like we don't implicitly say something is a base 10 number, but we say something is a base 2 or base 5 or base 8 when it's not our default. Okay. Any other questions? No questions? Nobody seemed to be fascinated by the fact that we can now do arithmetic operations using transistors. Yep.
That's addition. How is subtraction done in binary?
Well, the next module talks about subtraction. So subtraction turns out to be very easy as well. You just flip one thing, and addition becomes subtraction. So we'll get to subtraction next week, because we're going to master addition first, and then we'll deal with subtraction. Okay. We have 5 minutes left, so I can introduce the concept of implementing all of this stuff using logic gates, half adders and full adders. I will do all that during the lab. Okay, so in today's lab is me implementing all of this stuff using LogicSim, using gates, using components, using in LogicSim. So it's going to be an interesting one. Okay, so when you look at these definitions, C, X, Y, how do we draw that? X, Y as input pins, AND gate, and this becomes the output. Easy peasy, huh? What about Q? Same way. Except Q involves a little bit more code here, and I'm not going to use exclusive OR simply because exclusive OR is a complicated gate, and I just want to boil it down to the simple components. So when you do that with exclusive OR, we have 2 input pins X and Y, and then we have 2 AND gates. One AND gate has a bubble here, one AND gate has a bubble here. Now, the individual bubbles as input into an AND gate can negate the respective inputs. Okay, so this is something that you can do in LogicSim, so you don't need to use explicit NOT gates. So X is going to be negated going into the first one, but it's going to be unnegated going into the second one, like that. And then Y is the opposite. It is unnegated going to the first one, but it is going to be negated going into the second one, like so. So each AND gate, okay, the top AND gate, is implementing the sub-expression to the left. The lower AND gate is implementing the sub-expression to the right. Okay. And we have to combine these two. You go like, oh, now we have a OR. Okay, instead of using addition, we're using an OR. Now we can do that only because you can only have a carry from one up to one source, but not both. Let me say that one more time. When you're dealing with this particular situation, oh, well, it's okay. Never mind. I was confusing myself with something else that we have to talk about too. Okay, so this is the OR, which is represented by this thing here. So this becomes the output, which is Q. Are we doing okay so far with this? Yep.
That's adding row 2 and row 3, right?
That is going to be, well, C is not used by itself in a particular row. It is always used with something else in a row. But these are the lowest level components. Okay?
But not like the not X and Y, that's row 2, right?
Yeah, not X and Y is done by this gate. X and not Y is done by this gate.
Okay. So that's row 2 and row 3, right?
Row 2 and row 3 of the truth table, yes.
Okay.
Yep. Okay, and let me take a look at the time. 19, so we're almost running out of time here. There we go. Okay, so now we want to look at this and go like, okay, what about the construction of an adder? This is pretty easy, right? It's just R. We know how to do R already. This is just R all by itself. This one is a little bit more complicated because it has got a C on one side and a C on the other side. So the trick to do this one, and by the way, this R can feed into this R here, because they are the same. These two are the same. So this one here is a little bit complicated, because what about this plus here? That plus, in the general setting, is an arithmetic addition. But we want to convert it into logical operation. So we look at this and go like, we'll turn it into an OR. Now there's a reason why we can turn this into an OR. Because you cannot have carry coming from both sources. Mathematically speaking, you can only have a carry coming from one of these two sources, up to one of these two. So that's why you can replace the arithmetic addition here with a logical disjunction or logical OR. That would actually work. So once you replace this plus with a logical OR, now we can do everything in logic gates. Yeah, it's really kind of cool. Okay, so I'll give you guys a short break of about 10 minutes, and then after that we'll be in room 128, and I'll be doing all of this stuff here. I'll be constructing the actual adder in Logisim that actually works.
When are you gonna open them?
Huh?
When are you gonna open them?
I'm gonna go there right away after I shut down.
So